Welcome to a lesson with Dr. Powell. Let's discuss how the idea of projection of one vector visually onto another one can be thought of as a linear transformation. Well, first of all, what happens if you take two vectors and you add them together? So tail to tip. Well, is it not true that the projection of this one plus the projection of this one is the projection of the sum of the two vectors? Visually, that should be apparent. So projection is an additive function, meaning you add two things on the input, it's like adding two things on the output, adding the two projection lengths together. If you're thinking about an orthogonal or perpendicular projection downward. So even in more dimensions than two, we can think of projection is an additive function. Is it scalable? Meaning, if we rescale the input, does it rescale the output? Well, that should be pretty clear by similar triangles. If you multiply so this is a right triangle. If you multiply this by a certain constant, you've multiplied all your sides by the same constant. So therefore, it's also scalable, and therefore it is a linear function, or a linear transformation, rather. So knowing it's a linear transformation actually tells us a lot about how to compute projections. All right, so let's just, let's think of, for instance, suppose that we had, let's give an example. Let's suppose we're in R2. Okay, so let's suppose that we have a vector, suppose it comes to the point 3, 2, and we want to project it onto, maybe we want to project it onto something coming out over here. Maybe it's maybe at 4, -1, say. Okay, let's project it. Let's see what that projection would be. All right, so we're going to think of a projection onto this line right here, the line where 4, -1 is. We'll think of that as our function. All right, so our projection function we'll call f, and then we're projecting it. This f is defined specifically for the line that this vector right here is on. Okay, so projection down there. So to describe this function as a matrix, we simply need to know a few things. We need to just, well, two things. We just need to know the image of E. We know it's a linear transformation, so it can be written as a matrix. We just need to know the image of E1 and the image of E2. Okay, so to help us out here with this, we're going to do the following. We're going to turn this vector right here into a unit vector. So we simply divide by its length. Its length in the Pythagorean theorem can be determined simply by thinking, okay, that's a length of 1, that's a length of 4, and let's just find the length of the hypotenuse, which is 1 plus 16 square rooted, so square root of 17. So we get, okay, so what we end up getting is we get a unit vector in that direction. Suppose we just divide by the length, 4 over square root of 17, -1 over square root of 17. So we just take this vector divided by its length. It's now a unit vector. And let's just think about what happens. If we take E1, which is 1, 0, and we want to know how that projects onto the line, right? Let's think about that. Maybe, do this a little bit bigger. So we have this vector, which is 1, 0, and then we have this unit vector down here. Let's see, maybe make it actually look like a unit vector here, or have the same length here of some kind. So it kind of swings like that. So let's think about what happens if this, maybe make it a little bit longer so you can kind of visualize what's going on. So this guy is going to come down here and project right there. Now notice that if this guy projects right here, since both of these have the same length, length 1, because we made that a unit vector, projecting it this way or that way is actually the exact same, which is kind of interesting. So that means that projecting this vector onto E1 is the same as projecting E1 onto this vector. So the projection of E1 onto here should be the exact same as, well, let's think about this right here. It's 4 squared root of 17, right? Okay. Now, if we're thinking of projection, projection actually is a map that goes to R. Okay, in this particular case, because we're thinking about component length or projection length. So let's just think about length for a minute. So that means E1 will be sent to this value right here, actually. And that has to do because of this symmetry here, because we made that a unit vector. So going this way is the same as going that way. Okay, so we have f of E1. Now let's find f of E2. So what is the projection of 0, 1 onto that line? Now it's going to be a negative projection. Apparently, it's going to be down here. Okay, as we do that projection. So how are we going to do that? Well, let's think about how this works right now as we go along. Okay, so it's the same idea. So the projection here will be the same. Let's see, along that line, right there, right. So the projection one way should be the same as the projection going the other way. So actually, the projection, but remember, we're doing this projection, this line right here, onto that, which actually notices another negative value again, because the projection of one is, by the symmetry idea, is the projection of the other because they're both unit lengths by congruent triangles, same, with the angles and the sides and so forth. So it looks like this value right here is actually that projection. So this is kind of interesting. So in the column interpretation, if we input this into the projection function, 3, 2, simply what we get is just this times 3 plus that times that. This is sometimes called, or this is called a Euclidean dot product, or a dot product here. 4 root 17 times 3 plus negative 1 root 17 times 2. So if you take a vector, you make it into a unit vector, and then you dot it with things. That's the same thing as having a projection function onto the line determined by that vector. So think of this as the ground, and this is really a matrix function when we have putting input, and you end up getting your projections. Now, one nice thing about this is, see this dot product of this and this, and this, so this projection function right here. Now, if we were to multiply this back to the actual vector that we had, like 4, negative 1, this is just a rescaling. What is that doing? That's just a rescaling of projection. So if you make a dot product of, with a vector, that's like a matrix function, which, and like this is like 4 and negative 1 as a matrix. It's a matrix function, and that matrix function is just rescaling a projection. So in particular, let's think of that function, that rescaled projection, which goes from R2 to R, rescaled projection, which is just determined by 4, negative 1. So where we just take this and multiply it by square root of 17 to get this. So rescaled projection, that's an R, sorry. R, I didn't mean R2, I just meant R. So projection because it's projection length of any vector in R2 to that one. And it's a function, it's just a dot product thing. You do A, B, and then you would end up getting it out. Now, what is now a rescaled projection being 0 would mean what? That would mean that we would be perpendicular to that. That's kind of interesting, because that means that the fiber over 0 of this function is simply equal to all vectors that are orthogonal or perpendicular to the original vector. meaning that everything that makes this 0, so is the 0 fiber over 0, is actually what's orthogonal to it. So if you take any vector, defining dot product this way gives you, or this projection this way, this is a rescaled projection function. If we just take the vector like this and just do a dot product with it. So whenever it's equal to 0, we have things that are perpendicular to it. Thanks for watching.